Well, here we go. 7.03 Chemical Formulas. Yes, today you guys are going to learn how to write formulas for chemical substances. Aren't you excited? Because I know I am. By the way, what the heck is IUPAC? That stands for the International Union of Pure and Applied Chemistry. And this is the very organization that has standardized the practice of formula writing and naming across the world, hence the word international in the name. So, you can actually go to iupac.org to find out more information. If you want to complain because you don't like the way the naming system is set up, you can contact them. I don't think you're going to get anywhere, but it is what it is. All right. So, the reason we're going to use this, so once again, we're going to be able to name substances in such a way that anyone around the world can understand what we're talking about. So, if I need to order sodium phosphate, I can order it from anywhere in the world. If I use sodium phosphate or Na3PO4, people are going to understand what I'm talking about, or at least people who've learned what I'm about to show you. When you're given the name of a substance, it gives you the ability to recreate what the formula of the substance is. It's kind of a recipe. And especially when we get into organic compounds, when we name organic compounds at the end of this course, you're going to see how this is exactly like a recipe because you're able to name extremely complex molecules with a relatively simple naming system. Okay, so formula writing. When you write the formula for any substances, the ion charges cancel out. All the positive charges cancel out the negative charges, and the charges add up to zero. You always write the symbol and name of the positive ion first, and then the negative ion second. Always, always, always. Okay, so when is this not the case as far as we're concerned? Never! Okay. You use subscripts like H2O are used to tell you how many ions there are in the formula. And if there's only one, you don't write the subscript. For example, water is not H2O1, it's just H2O. The 1 is assumed, just like in algebra, you wouldn't say 1x, you'd just say X marks the spot. Okay, so if there's only one ion in the formula, you don't use a subscript. So here's how to write binary formulas. Since the charges are the same, +1 and -1, they already add up to 0. Therefore, 1x and 1y is all there is in the formula. So if you're going to bond sodium ions and chloride ions together, they're +1 and -1, the charges add up to 0, just 1 to 1. So NaCl will be the formula of this substance. And this is true anytime the positive charges and negative charges are the same right out of the box. So if the charges are +2 and -2, then they'll bond in a 1-to-1 ratio. For example, when calcium and oxide bond together, they bond together in a 1-to-1 ratio. And the same thing will happen if +3 and -3. So we're going to still have a 1-to-1 ratio when we bond aluminum +3 to phosphide -3. It'll exist in a 1-to-1 ratio. That's easy. But what if the charges are a different size? For example, what if one is +2 and the other is -1? Well, remember, we have to make this all add up to 0. So how many of the smaller charges do we need to cancel out the larger charge? The larger charge is +2. The smaller charge is -1. We need 2 ions with a -1 charge to give us that -2 charge. Therefore, for every 1x plus 2 ion, there will be 2 y-1 ions. So, for example, when we bond iron 2 with bromide, the reason I call it iron 2 is because iron has 2 different charges, so I had to specify which one I was using here. In order to cancel out the +2 charge, bromide has to be a total of -2, and it will take 2 bromide ions to accomplish this. Same thing if the charges are +3 and -1, except this time it will take 3 -1s to give you -3, which is what it takes to cancel out a +3. So when we have nickel, 3, and fluoride, we're going to need 3 fluoride ions to cancel out the 1 nickel ion. And the same is true if the negative ion is the larger size. We'll need 2 plus 1s to cancel out the minus 2. So the formula for silver sulfide would be Ag2S. We need 2 positive 1s to cancel out the negative 2. X is plus 1, Y is minus 3. We're going to need 3 positive 1s to cancel out the negative 3. So when we bond potassium with nitride, our formula will be K3N. I want you to notice something very interesting here. With the exception of the ions whose charges are the same size, if the ion charges are different, notice that whatever the charge of the positive ion is, that's how many negative ions there are. And whatever the charge of the negative ion is, that's how many positive ions there are. This leads to a technique called drop and swap, which will make your formula writing so much easier. For example, if we drop and swap, if the number of x's is whatever the charge of y is, and the number of y's is whatever the charge of x is, it's kind of like cross multiplying, because 2 times plus 3 is plus 6, and 3 times minus 2 is minus 6. So you see, by dropping and swapping, the charges cancel out, just like cross multiplying to find the least common denominator. So to form scandium oxide, we drop and swap, and we get Sc2O3. Now, you're not going to be learning this in a vacuum, because in the next unit, you're going to be applying this to actually completing and balancing chemical reactions. So your ability to write a formula is not just for the sake of writing a formula. There's a practical use for it. So what if the charges are flip-flop, plus 2 and minus 3? Well, again, just drop and swap. 3 times plus 2 is plus 6. 2 times minus 3 is minus 6. So if we have magnesium nitride, we just drop and swap the charges, and there we go. Now, there's a case where drop and swap will need one additional step. If we have plus 4 and minus 2, if we drop and swap, we'll get X2Y4. But we can do better than that. It takes 2 minus 2's to cancel out a plus 4. So therefore, we can simplify X2Y4 to XY2. So if we're going to react lead-4 with oxide, we're going to need 2 negative 2's to cancel out the positive 4. We could say Pb2O4, but then we would simplify it to PbO2. When you're dealing with an ionic compound, you must simplify the formula. This is what's called an empirical formula. So the crossover technique, drop and swap, I'll just show you very quickly. You just cross over the numbers of the charges and then simplify if you need to. So since the charges are the same size, they just cancel out. Since the charges are different, we drop and we swap the numbers and eliminate the ones. The charges are different, so we drop and swap the numbers, we eliminate the 1. We drop and swap the numbers, eliminate the 1. We drop and swap the numbers, eliminate the 1. We drop and swap the numbers, eliminate the 1. Aha! Whee! Woohoo! So you see, you're just taking the charges, not the symbols, not the pluses or the minuses, just the numbers, and you're swapping them. Of course, if the charge is the same size, you can just cancel it out. But if you do decide to drop and swap, don't forget to simplify. You can drop and swap, but if you can simplify, you must simplify. So the crossover technique, the drop and swap method, drop and swap, just cross over the charge on top. Drop and swap, drop and swap. When the charges cancel out, then you can stop. Oh, yes. So, how do we write the formula given the name? Well, for this, you're going to need the periodic table. You can't do this without the periodic table. Trying to write or name a formula without the periodic table is like trying to brush your teeth with a chainsaw. It's pointless and it's painful. Potassium sulfide, what we need to do is look up the charges of each on the periodic table. And according to the periodic table, potassium is +1 and sulfide is -2. So when we drop and swap, we get K2S. Lithium chloride. If we look on the periodic table, we'll see that lithium is +1 and chloride is -1. Their charges just cancel out because they're the same size to give us lithium chloride. Silver oxide, if you look on the periodic table, we'll see that silver is +1 and oxide is -2. If while we're doing this, you want to verify this, just simply pause the video, go to your periodic table, and verify it for yourself. Since the charges aren't the same, we're going to drop and swap the numbers. And remember, we eliminate the 1. For copper 2 fluoride, the reason we're going to use a Roman numeral 2 is because copper has two possible charges, +1 and +2. This is telling us that we need to use the +2 variety of copper. Now, a common mistake people make is to say, the Roman numeral tells me which of the charges to use, like 1 means it's the first one that's listed and 2 means it's the second one that's listed. No, that's a lie. The periodic table gives you what the charges are, and the Roman numeral refers to the exact charge itself. So copper 2 specifically refers to copper with a charge of +2. And we drop and swap because the charges aren't the same. Same thing with iron 3 sulfide. Iron has two charges, +2 and +3. This is telling us to use iron with the +3 charge. And when we drop and swap, that gives us the formula of iron 3 sulfide. Next example, gold can be +1 or +3. This is telling us to use the +1 variety of it. And when we drop and swap, we get our formula. You see, it's very easy. You just have to make sure that you look this stuff up on the periodic table. Now, I don't have to look it up most of the time because I've been doing this for about 40 years between high school chemistry and college chemistry and teaching it. So I kind of know what the charges are, but you're just starting out on this journey. You don't know what these charges are yet. So until you've done this enough that it becomes like tying your shoes, you don't have to think about the charge of oxygen being -2 in a compound. Look it up. Look it up. It's good practice. And the more of these you do, eventually you'll get to the point where you'll just know nickel can be +2 or +3. You won't have to look it up. Zinc bromide, zinc only has one charge. That's why there's no Roman numeral for it. And therefore, we look up that charge and then we drop and swap to write the formula. Lead can be either +2 or +4. This is telling us to use the +2 variety. And since the charges are the same size, we just cancel them out. Lead 4 oxide is telling us that we need to use the +4 variety of lead. And you can drop and swap, but you have to remember to simplify. Pb2O4 simplifies to PbO2. Get that back. All right. Now, we can also reverse the crossover if we want to figure out what the charge is for the purposes of writing the formula. However, I'm going to skip past this to show you something far more useful. So I'm just going to skip past this and go right to how to write the name from the formula. Okay, here we go. What you do first is you always write the name of the positive ion first. And if the positive ion can have more than one charge, you have to specify what its charge is in that specific compound. Then you write the name of the negative ion, which ends in IDE. Fluoride, chloride, bromide, oxide, sulfide, and so on. So if we look on the periodic table, we'll notice that sodium has only one charge, and therefore no Roman numeral is needed for it, and therefore NaF is simply sodium fluoride, also known as the source of fluoride that's in your toothpaste. Zinc bromide. Well, I kind of gave away the farm here, didn't I? I actually told you its name. So why is it zinc bromide? Well, zinc only has one charge on the periodic table. It's plus 2. And since there isn't an additional charge on here, like let's say plus 3, a Roman numeral is not needed after its name. So zinc bromide will be the name of this compound. For Fe2O3, now we get into the fun. Fe can be plus 2 or plus 3. Now, which of these charges would it have been to drop and swap a 3 down to the oxygen? A plus 2 would drop and swap a 2, and then it would simplify. Plus 3 drops and swaps and gives you that 3. Therefore, it's iron 3 oxide. Iron with a charge of plus 3 was needed to make this compound. Now, the most common mistake people make is to use the number of irons as their Roman numeral. That's not what the Roman numeral means. The Roman numeral is saying, what is the charge of each iron? Now, you could approach it from this direction too. Oxygen is oxide rather, is minus 2. 3 times minus 2 is minus 6. What times 2 is plus 6 to cancel it out? 2 times plus 3 is plus 6. So it's iron 3 oxide. So either way will work. FeO. Well, now we have iron plus 2 and iron plus 3. Oxide is minus 2. What does iron have to be for the charges to cancel out? Minus 2 is canceled out by plus 2. Therefore, iron 2 oxide would be the name of this compound. This is why we can't just call them iron oxide. There are two different kinds of compounds you get when you react iron with oxygen. Next example, Ag. Well, silver has only one possible charge, and therefore we can just call this silver chloride. Cu, copper, has multiple charges, plus 1 and plus 2. Which charge will drop and swap and give you a 2 down here? Plus 2. Chloride is minus 1. 2 times minus 1 is minus 2. What cancels out of minus 2? Plus 2. And therefore, there are a couple of ways of arriving at the fact that the copper is the plus 2 version of the copper 2 chloride. As opposed to this, chloride is minus 1. Therefore, copper has to be plus 1 to cancel it out. Ki. Potassium has only one charge, and therefore we can call this potassium iodide. Iodine becomes iodide. PbS2. Pb is lead. Lead has multiple charges. Now, it would be very tempting to call this lead 2 sulfide. However, you have to be very careful with lead because what happens is even numbers easily cancel each other out. Sulfide's charge is minus 2. What's 2 times minus 2? Minus 4. What cancels out a minus 4? A plus 4. So in this case, it's lead 4 sulfide. That's the tricky bit, is coming up with the Roman numeral. But the more of them you do, the better at it you're going to get. Okay, so all of these so far have been what are called binary compounds. They're compounds that are made only of two elements: sodium and fluorine, zinc and bromine, iron and oxygen, and so on. There is also a class of compounds called ternary compounds. These contain 3 or more elements in them, and they involve the use of an ion that you can find on reference table E, New York State reference tables. These are called polyatomic ions. These are molecules that have been broken in some way. Molecules have no charge, but if you give them too many electrons or too few, then the charge can develop. And you can see that the majority of the ions that are listed here are negative in charge. They're molecules that have an excess of electrons. A few of them are positive in charge. They have a deficit of electrons. Hydronium and ammonium and mercury 1. Because 2 times, how many, plus 2 divided by 2 mercuries. Each mercury is plus 1. That's why it's called mercury 1. Now, I also want you to notice that a lot of these have endings that include ATE and ITE. And a lot of them also have oxygen in them. Let's look at the chlorine and oxide formulas here. Okay, so we have chlorate. Chlorate is ClO3. Add one more oxygen, we get per. Per is short for hyper. Hyper means over and above. Hyperchlorate or perchlorate. So perchlorate has one more oxygen than chlorate. Ite will always have one less oxygen than ate. Chlorite has one less oxygen than chlorate. Nitrite has one less oxygen than nitrate. Sulfite has one less oxygen than sulfate. And hypo means less than. So chlorite has two oxygens. Less than two oxygens would be one oxygen. So there is a method to the madness. So all you have to do is, if you have a polyatomic ion, just look on this chart for what its formula is. However, there is one additional thing you have to do for these formulas. The drop and swap technique is identical. The writing of the formulas is easy. However, if you drop and swap any number other than 1 after one of these polyatomic ions, you have to put the polyatomic ion in parentheses first. So what exactly does that mean? Crossing over anything greater than 1, put parentheses around the polyatomic ions formula. All right, here's how it works. Potassium sulfate is made of potassium and a sulfate ion, SO4 minus 2. And again, we can just look that up. Sulfate is SO4 minus 2. So if you want to have your reference tables handy while I do this so you can verify it, just pause the video and grab your reference tables. You don't even have to wait because I'm just going to move on now. Okay, so we have K plus 2 and SO4 minus 2. We're going to drop and swap the 2 to the potassium, but we're only going to drop and swap a 1, and we don't even write that 1. So our formula is K2SO4. Lithium chlorite, they're both the same charge, they're both the same size charge, so they just cancel out. We don't have to drop and swap anything. Silver oxalate, well, again, we're going to drop and swap the 2, but a 1 that we're not even going to write will drop and swap to the oxalate. So that makes the formula writing easy. However, this time we're going to have to drop and swap something after the polyatomic ion symbol. So copper 2 nitrate, copper is plus 2, nitrate's minus 1. This minus 1 will drop and swap and not be written. This 2 will drop and swap. So what are you going to write? NO32? No, we want to show that we have 2 of these NO3s. To do that, we place the NO3 in parentheses and the 2 outside the parentheses. That's what I mean by if you drop and swap anything other than a 1, you have to put parentheses around the polyatomic ion first. If these parentheses weren't here, this would be NO32. Instead of showing that we have 2 nitrates, which show that we have 1 nitrogen and 32 oxygens. That's the way the standard is set. So you need those parentheses. So here's another example. Iron 3 has a charge of plus 3, and sulfite is SO3 minus 2. So we'll drop and swap. We'll put the 2 after the Fe and the 3 after the SO3. But we don't want it to read SO33, so we put parentheses around the SO3 and the 3 that we're dropping and swapping outside of it. Next example, gold 1 phosphate. Now, in this example, we'd be dropping and swapping a 1, which doesn't get written, so we don't need parentheses around the phosphate ion's formula. Zinc acetate. Zinc has a plus 2 charge, and you'll notice that there's a couple of different ways of writing the acetate ion. Use whichever one you prefer. The technique will be the same. Since we're dropping and swapping a 2, put parentheses around the C2H3O2 first, and then place the 2 that you're dropping and swapping outside those parentheses. Next example, lead 2 carbonate. Well, they're both the same size charge. Therefore, they just cancel out. No parentheses needed. No drop and swap needed. Lead 4 carbonate, now the charges are the same. We could drop and swap and make this Pb2CO34, but a 2 to 4 ratio would simplify to a 1 to 2 ratio. We need two negative 2's to make negative 4, which is what it takes to cancel out a positive 4. That's how to use parentheses around polyatomic ion formulas. Now, how do we write the name from the formula? Well, it's exactly the same thing we did before. We simply just write the name of the positive ion with the Roman numeral if we need it, and then the name of the negative ion, but this time we just have to look it up on reference table E, or whatever polyatomic ion chart you happen to have available if you're not in New York State. So, NaNO3, Na has only one charge, so no Roman numeral is needed. Sodium nitrate. Easy peasy. ZnClO4 zinc has only one charge, so no Roman numeral is needed, and ClO4 is the perchlorate ion. Now, iron has more than one charge, +2 or +3. Which one would drop and swap and give you a 3 here? +3. The other way to look at it is carbonate is -2. You can look that up. 3 times -2 is -6. 2 times what is +6? +3. So either way you look at it, it's iron 3 carbonate. FeCr2O7. Iron is +2, and you may be thinking, but wait, we dropped and swapped a 7. Because if we had dropped and swapped anything, there'd be parentheses around this, and the number would be outside the parentheses, like in the previous two examples. That means there's only one dichromate ion. So what we need to do is look it up on reference table E. And according to table E, go ahead and look for yourself if you don't believe me. The dichromate ion's charge is -2. And what cancels out a -2? A +2. This is iron 2 dichromate. Ag, silver, has only one charge, and so we can just call this silver hydroxide. Now, it can be a little confusing. This is O and this is H, and yet in the name, the H comes before the O. Hydroxide is OH, not HO. Copper has more than one charge. Which one will drop and swap the 2 down here? +2 will. The other way we can look at it is ClO has a charge of -1. 2 times -1 is -2. What cancels out a -2? A +2. So either way you look at it, it's copper 2 hypochlorite. CuClO. Now I put the parentheses here for a reason. You don't put the parentheses if you're not dropping and swapping anything. But just to show you, ClO's charge is -1. So what will copper's charge be? +1. Typically, this would be written without the parentheses. It would be CuClO. I'm putting the parentheses here to show you where the polyatomic ion is. When you write the formula, if you're not dropping and swapping, don't write those parentheses. All right. NH4. Well, if we go to reference table E, we'll notice that NH4's name is ammonium. And it's bonded to oxygen, so it's ammonium oxide. So again, the only trick is to figure out what the Roman numeral is. Other than that, you're just copying down names. What about this? Well, again, remember, lead can be tricky. You might be tempted to call it lead 2 because there's a 2 down here. However, even numbers cancel out easily. Sulfate's charge is -2. 2 times -2 is -4. What does it take to cancel out a -4? A +4. So lead would be lead 4 sulfate. Watch out for lead. Lead's tricky. That is how you do the formula writing and naming for ionic compounds. Come back next time. I'll miss you until then. Actually, if you're not in my class, I don't even know you. But I still wish you well, and I still want to say bye.